We've been looking at alternative hypotheses that go one way or the other. So either like our alternative hypothesis has been greater than or it's been less than. However, there also is, if you can't decide which way to go or if the problem doesn't specifically tell you which way to go, you can also do not equal to. Okay, these have a specific name. They are called one-sided hypotheses because we are literally looking in one direction. I'm either looking greater than or I'm looking less than. And this one is a two-sided because since I'm looking just for it to be different, not equal to, it could either be greater than or it could be less than. Okay, doing two-sided hypotheses is very similar to doing one-sided ones with just a few minor differences, mainly in how we calculate the p-value. So we have an example. When the accounting firm AJL and Associates audits a company's financial records for fraud, they often use a test based on Binford's law. Binford's law states that the distribution of first digits in many real-life sources of data is not uniform. So, in fact, when there is no fraud, about 30.1% of numbers in financial records begin with the digit 1. However, if the proportion of first digits that are 1 is significantly different, then they do a much thorough investigation of the company because then they suspect fraud because even though you're trying to be random, if you're making up records, usually you're not. So let's suppose that they look at a random sample of 300 expenses from a company's financial record and they only see 68 expenses that begin with the digit 1. The question is, should they do a more thorough investigation of this company? Okay, notice that here they're not telling us specifically to do a test or an interval, so really we get to pick. And we'll kind of work through it both ways just so you can see how it works either way and kind of to review Chapter 8 as well. Okay, so we want to make sure we go through all 4 of our steps, and let's do this with a significance test first, and then we'll come back and do it with an interval. So our significance test, first step is state. We want to test the following. The null would be that the proportion would be equal to 0.301 because statement of no difference. If this is what the proportion of first digits usually is, then that's what it should be in the records they're looking at. And then we have the alternative, which is just that it's something different. Not necessarily that it's less than, not necessarily that it's greater than. We just know that it should be different. At the alpha equals, and since they didn't give us a alpha level, we're going to say 0.05, where p is equal to the proportion of first digits that are 1. Okay, so then we want to plan. We want to do a 1 sample z-test for p. I need to check my conditions. Random, normal, independent. Okay, and I'm going to go back and look at the problem here. It is normal because it says that they take a random sample. I need to know that n is 300. And while I don't need to know p hat yet, let's just go ahead and calculate it. That would be 68 out of 300, which would be 0.227. Okay, so they tell us that they are taking a random sample. So that's how their random condition is met. I'm still dealing with proportions here, so for normal, I need to say n times p. So that's 300 times the 0.301 that we're assuming is true. And that gives me 90.3, which is greater than or equal to 10. And n times 1 minus p, so that would be 300 times 1 minus 0.301, which is 209.7, which is also greater than or equal to 10. So it's normal. And I can assume that there are at least 3,000 expenses in this report, because I need the 10% condition. So 10% of 3,000 is the 300 that my sample size was. Okay, so all of my conditions are met. Then I am ready to do the do statement, where I find my z-score. Okay, my value, which we said was 0.227, that's the 68 over 300, minus what we assume it really is, because that would be the mean of our sampling distribution, divided by the standard deviation of our sampling distribution, which would be 0.301 times 1 minus 0.301, divided by the sample size, which is 300, take the square root of all that. So basically this is telling us how far away from the true mean, okay, which is the true proportion, is the proportion that we have in terms of these standard deviations. And what we're going to get is a negative 2.79. I'm glad it's negative, because that tells me that one of the ways that I did this right, because my p hat was below the actual p. So then I find the p-value. Okay, the p-value represents the probability that I am going to get a p hat less than or equal to 0.227. Okay, and that p-value, when I look at table A, or when I do this on my calculator, is 0.0026. Okay, however, here's the thing we want to look at before we conclude. This is a two-sided. I only did this for less than or equal to, and there's a reason I only did it for one, because if you look at the picture, this is my actual, what we assume to be the true proportion, right? It's the mean of all of my p-hats, which is my true proportion. Okay, I want to know what is the probability that I'm going to be different. So not just greater than and not just less than. What is the probability that I would get one that is as different from this as the 0.227 that I got? So in addition to looking at the probability that I'm going to get something less than that, I need to look at the probability that I'm going to get greater than the equivalent on the other side too, because I just wanted to know if it was not equal to. So that includes both less than and greater than. Okay, so the equivalent over here is 0.375. Okay, that's the same distance from here to here as from here to here. Okay, and you would think I would have to do my z-score all over again and find my area, but I don't, because this is normal, so I know that it is symmetric. So I know that this area is equal to this area. So if this area is 0.0026, then that means this area is 0.0026. Okay, so instead of having to find two areas, because I know that my normal curve is symmetric, when I do my p-value, what I really need to do is say this times 2. That is the only difference between doing a two-sided test and doing a one-sided test, is that I need to account for the fact that I have probability in both ends, and I need to multiply this p-value times 2, which makes ours 0.0052. And this is the p-value that I work with, and this is the one that I compare to my alpha. So then when I conclude, I do the same fill in the blank that we always do. Because our p-value, 0.0052, is less than the alpha, we reject the null hypothesis. Therefore, we have, and I've run out of room, so I'm going to go up here. Convincing evidence that the firm should do a more thorough investigation. Okay, notice that because it's a proportion one, all of my steps were exactly the same, my conditions were the same. The only difference is that I need to multiply that p-value by 2. Okay, that's the only difference. Okay, let's compare what we just did to kind of a confidence interval. So we have here our sampling distribution and our two-sided test for alpha equals 0.05 means that my total area on both sides here needs to be under 0.05. Okay, so I know that this is symmetric. Okay, about my mean here, which is p, the mean of all my p-hats. Okay, and I know that my alpha level, because I'm multiplying my p-hat by 2 to account for this, means that, okay, half of my probability is on this side and half of it is on this side. So this theoretically means that the top 2.5% and the bottom 2.5% of p-hats will result in a rejection. Okay, if I have 2.5% down here and 2.5% here, what percentage is in the middle? Okay, well hopefully you can do the math and subtract from 1 and notice that this is then 0.95. Where else do we see the 95% middle of the data? Okay, in a 95% confidence interval. So if we have a two-sided test, okay, confidence intervals actually give us more information than the test does, because a confidence interval, and I'm just going to abbreviate that CI, okay, confidence interval will give you the values that will not result in rejection. Okay, the confidence interval gives you values that will not result in rejecting the null. Okay, or that will reject and failing to reject the null. So it gives you values that will not reject the null. And the reason that that gives us more information is that in a significance test, I either reject it or I fail to reject it, but it doesn't give me any idea about what the value actually might be. Using a confidence interval, as long as it's a two-sided situation, okay, confidence intervals can only be used for two-sided situations. Can not only help me to decide to either reject or fail to reject, they can also give me an idea about what the value might be. So they can only be used in two-sided, not equal to situations. So if I notice in my situation that I clearly am going like one way or the other, clearly looking for more ones or I'm clearly looking for less ones, then a confidence interval is not going to help me. But if I'm just looking for there to be a different amount of ones, then a confidence interval might help me. So let's go back through our Benford's Law problem here and do it with a confidence interval this time, because I know it's a not equal to situation. So let's see how this would work with a confidence interval. Okay, so remember, same four steps. They look a little bit different though. We want to estimate the true proportion of numbers that begin with 1 in these financial records. And if my if my alpha was a 5%, then that means my confidence interval needs to be 95%. So at the 95% confidence level. So then I have to go to plan, which requires me to say what I would like to do. And since it's a confidence interval, I can either say that I want to use the confidence interval, which is a 1 sample interval, z-interval for p. Or I can just write the formula, which I know would be my point estimate p hat, my sample statistic, plus or minus my z-score times my standard deviation of p hat, which is p times 1 minus p divided by n. Okay, so then I need to do my conditions. Normal. Because we are doing an interval now, we don't have that null hypothesis for us to assume is true. So even when I do my normal condition, I need to make sure that I use my p hat instead of p. Okay, so your normal condition is going to be the only condition. You do it the same way, but it's going to be different values than it was with the test, because in the test we're assuming our null hypothesis is true, so we assume we have the value of p, and in these we don't have the value of p because we don't have a null hypothesis. So this would be 300 times the 68 over 300, which would just be 68. And n times 1 minus p hat would be 300 times 232 over 300, which would be just 232. And both of these are greater than or equal to 10, so our normal condition is met. Okay, random. You chose a random sample of entries. And independent, we can assume there are at least 3,000 entries. Okay, notice again, these conditions are exactly the same for doing an interval versus doing a test. They are no different, exactly the same. Okay, so then I do my do statement, and in this time, it's just a matter of plugging in my interval. My p hat value was 0.227, plus or minus. I do need to look up my z star. Okay, I do need to find out what my z star is for a 95% confidence level. So I either go to table A or I do inverse norm. Those are my two options. Okay, table A or inverse norm on the calculator. And hopefully this is one you'll just memorize because it's so common. Whenever it's a 95% confidence interval, my z value, my z score, 1.96 times the square root of okay, and in this time, because I don't have a null hypothesis to use, I have to use my p hat value. So this, instead of being the 0.301 like it was in the test, is 0.227 times 1 minus 0.227 divided by 300. So I plug this into the calculator, and I do this plus all this, and I do this minus all this, and I end up with this interval, which is 0.180, comma 0.227. 0.274. Okay, and I conclude we are 95% confident that the true proportion of numbers that begin with 1 in this company's finances are between, I guess that should be is, signs prove or grammar, is between 0.180 and 0.274. Because this is below 0.301, a more thorough investigation is needed. I'm running out of room here, but okay. The reason that we can conclude this is because I know that the 0.301 was the number that they said that should be. Okay, this not only tells me that the numbers for this that are not going to give me a rejection is below, does not include 0.301. It also tells me it's below. So I am getting more information from this interval than I got from my test. The only thing I got from my test was that, yes, I need more investigation. This one tells me not only do I need more investigation because 0.301 is not in this interval, okay, because this is what we believe the proportion of numbers that begin with 1 in this company's finances are, and 0.301 is not in it. Okay, it also tells me that this company is using fewer 1s than are normally found. Okay, so it gives me that extra piece of information that a test doesn't. So when you are doing a two-sided test, an interval will not only tell you the same thing, it will actually give you more information.